Hi, how's it going? Hello everyone. All over YouTube are videos where people supposedly make free energy generators or simply a 5 to 10 kilowatt generator out of a handful of small, cheap parts. I picked one of those videos to follow along with, and today I'm going to somewhat closely replicate a supposedly 10 kilowatt generator, and I'm actually going to test it. As we go, I'll explain the parts, how they work, and at the end, I'll even show one way the supposed results could be faked. I know, that's a bit of a spoiler, but as I explain each step, it will become obvious why I have a plan already lined up to show one possible way the results could be faked. Hopefully this video isn't too dry and boring, but I wanted to dig into the details a bit. So let's make some room on the desk and get started. Following along with the video I picked, I'll start by wrapping 2 lengths of wire around a bearing race. Virtually all of these contraptions seem to have coils of wire and often random magnets all over the place because apparently magnets are magic. The thing is, magnetism is key to making a generator work. At its most basic, a generator is just a magnetic field moving across a coil of wire or a coil of wire moving through a magnetic field. The magnetic field can come from permanent magnets or from an electromagnet. As a magnetic field moves across a coil of wire, a charge is induced. I currently have my meter connected to this coil measuring AC voltage. You can see that there is a small amount of voltage being induced into the coil just from the small magnetic fields in the room. But if I wave the magnet past the coil, you can see the voltage jumps up. And just like that, we generated a tiny bit of electricity. The movement of the magnetic field is a requirement. If the wire and magnetic field are static, you won't induce any voltage, even if the magnet is right against the wire. However, alternating current has a neat trick up its sleeve. When current flows through a coil, a magnetic field will quickly build around the coil. That's electromagnetism. When you de-energize the coil, the magnetic field collapses. Alternating current continuously changes polarity, crossing zero each time it does so. In the US, we have 60 Hz AC, so 60 times a second, the voltage builds, drops, crosses zero, builds up again in the opposite polarity, then drops to zero again. So a coil energized with AC has a constantly growing, collapsing, and polarity reversing magnetic field around it. Put 2 coils next to each other, and you have the beginnings of a transformer. One coil in a transformer is energized with alternating current, and as the magnetic field grows and collapses, the magnetic lines of flux are constantly moving back and forth across the other coil, inducing an AC voltage into that coil. A transformer does not work with DC voltage. When you apply a direct current to a coil, the magnetic field builds and then remains constant. It becomes a static magnetic field and no voltage will be induced into the other coil. So that's a very simplistic overview of how magnetism can induce voltage into a wire or coil and how transformers work. Getting back to our project, we now have 2 coils of wire wound around this bearing race, and the next step is a diode connecting the 2 ends of our windings. As we go, I should point out that the size of literally every component involved is absolutely laughable given the claim of 10 kilowatts. Based on the video, I believe it was a 6 amp diode that they used, so that's what I'm using. A diode is sort of like an electronic check valve. It blocks current flow in one direction and allows it in the other. If we manage to generate any voltage in these windings, it would be AC. Generating electricity via a moving coil or a moving magnetic field will produce AC. A simple way to think of it is to imagine that as a magnetic field approaches a wire or a coil, it will be kind of pushing the current one way, and as it passes the wire and moves away, it will sort of pull the current the other way. That's an oversimplification, but the point is, any voltage we generate in these windings would be AC. Putting the diode in series with the windings will half-wave rectify the AC voltage it generates. Since a diode blocks current in one direction and allows it in the other, it will block half of the AC sine wave. The output from a half-wave rectified winding will be a pulsing DC voltage. Picture an AC sine wave with the bottom chopped off. So putting this diode in place means that any output we could possibly get from these coils would be half-wave rectified DC. This design is already off to a terrible start because half-wave rectification blocks one whole side of the sine wave. This one step ensures that over half of the potential capability of these windings is being thrown away right off the bat. The next step is to hot glue a magnet to one side of our coil assembly. This step follows the template many of these videos use, where more magnets is more better because magnets are magic. It's an easy step, but it's a static magnet, so it's not going to do anything. In fact, before we move on, I'm going to go ahead and glue it to the board now because why not? And that brings us to the transformer. No surprise, but this transformer is woefully undersized considering the 10 kilowatt claim. The transformer I have here is roughly similar in size to the one in the video, and it is a 50 VA transformer. Even assuming a unity power factor, which is the best case scenario, that's still 0.5% of 10 kilowatts. Forget 10,000 watts, even 100 watts would be twice what this transformer can handle. Also remember that a transformer doesn't work with DC voltage, and any voltage we could possibly get out of these coils would be half-wave rectified because of this diode. Technically, it would be a pulsing DC, so it would result in a changing magnetic field within the transformer, not a static one. But when AC switches polarity, the polarity of the resulting field also reverses, and it sort of resets the magnetism in the transformer core. A pulsed DC never does this, so the magnetic field in the transformer can just build up until it reaches saturation, at which point the output would drop and the transformer could even fail. Basically, this transformer might be able to produce a small amount of output with a pulsed DC input, but if these coils actually manage to create any meaningful power, it would likely just burn up the transformer. Pulsed DC can be used in specific transformers, or if specific steps are taken to prevent the transformer from reaching saturation. But with this type of transformer and this application in general, it probably won't work at all, and it's definitely a ridiculously inefficient and ineffective way to do it. Honestly, if we were going to put power through the transformer anyway, we'd have been far better off to just leave the diode out and just send AC straight to the transformer. But they use the diode in the video, so we'll press on. The video shows that the 220 volt primary side of the transformer is used as the output, so that's the way I'm going to set it up here. We've barely moved on from the last reason this device couldn't work, and now we arrive at possibly the most nonsensical design element, which is saying something. This next step literally guarantees that this device will have zero ability to produce any power. The video shows a diode bridge rectifier installed between the bearing coil and the transformer. That makes zero sense for multiple reasons. First, any output would be DC already due to the diode between the windings. And this is a full-wave bridge rectifier, but you can't get back the part of the sine wave that's already been blocked by another diode. So at best, this component is totally pointless. But considering the rest of this device and where and how this rectifier is wired into the circuit, it's actually much worse than pointless. If we were to fully rectify the output of this coil to DC before the transformer, we'd just be guaranteeing that the transformer wouldn't function properly because full-wave rectified DC won't work in a transformer at all. But it gets even worse because the video clearly shows the bearing windings connected to the DC output side of the rectifier. And the transformer gets connected to the AC side. Initially, this might seem like it makes sense because any output from the bearing coil will be pulsing DC and a transformer works on AC. But all a rectifier like this is a small chip with 4 diodes built in. Bear with me, but I've actually drawn a crude diagram of how this device is set up. You can see on this side we have our bearing coils with the little diode in between the two, and the output of those windings goes to the positive and negative side of this rectifier. This is the diode bridge rectifier that is that next component I talked about. And all that's inside that are 4 diodes in this arrangement. Now normally, if you were to put AC into a rectifier like this, when the polarity is coming this way, it can go through this diode, pass out the positive side, come around, go back into the negative side, and come back out this side of the AC. When the polarity of the AC current reverses, it comes in this side, can pass through this diode, once again comes out the positive side, loops around, goes back in the negative, can come down here and go back on this side of the AC winding. So that's normally how it would work with input. And in that way, no matter which way the AC is coming into this, it's always coming out on the positive, positive, and negative, negative. So it's just a way of making it so that either way the pulse comes into this, it always comes out positive here, negative here. But if we apply a DC input into these two terminals, nothing or worse than nothing is going to happen. So assuming the diode was connected like this, which this is just an example, assuming the diode was connected this way, when these things are pulsing, any current that tries to come this way gets blocked by the diode, so this just does nothing, and any current that tries to come this way will be positive, and it will hit this terminal, which is positive, and it will simply just be blocked by these two diodes, and it can go nowhere. So in this orientation, that basically nothing will happen. Any current that is produced by these windings would be blocked 100%. If this diode were facing the other direction, then again, current in this direction is blocked by this diode, and then when current tries to flow in this direction, it's going to come into here, but it can pass through this diode this way and this diode this way. So this terminal and this terminal will both end up with the same potential. They're both energized by this one wire here and here. So since these are at the same potential, no current could possibly flow through this winding because these two are the same potential. You have to have a difference in potential in order for current to flow. This current coming this way is going to go through both of these diodes, make both of these the same potential. No current is going to flow through our transformer winding, but that current can continue on its merry way through these two diodes and just end up back here. So this would just end up just a complete short circuit. So depending on the polarity of this diode, based on where they have it wired, it would either completely block all output from this winding or completely short this winding out, once again preventing any output from this winding. So the addition of this rectifier and the way it's wired in guarantees this device cannot produce power, as if there weren't enough issues already. But the catastrophe of adding this rectifier doesn't stop there. The part number of this diode was clearly visible in the video, so I was able to get the exact same one, and it is rated at just 4 amps. In case the scale of the problem isn't obvious, let's put things into perspective. At 220 volts, which the video claims this device will produce, 10,000 watts would be just over 45 amps. That's far more than any component used could possibly handle. But like everything else about this device, it gets so much worse. Our little bearing coils are connected to the 12-volt side of the transformer. That insinuates that the expected voltage created by the coils would be around 12 volts before it goes to the transformer and is stepped up from 12 to 220 volts in the transformer. So the implication is that these coils are producing 10,000 watts at 12 volts. But 10,000 watts at 12 volts is over 800 amps. But even 100 watts at 12 volts is over 8 amps, which is 30% more than the diode can handle, twice what the rectifier can handle, and twice what this transformer can handle. It's just staggeringly absurd. But let's keep going. And despite everything I've said so far, I still am building it just like they show in the video, because I don't want there to be any question of, having not done it just the way they did it. And as with all of these devices, the output doesn't get connected directly to a load. No, it gets connected to a receptacle box that some lights can get plugged into, or in one video I saw, the output was connected to metal studs sticking out of the board, and then the load got connected to those studs. Of course, this gives the ability for those studs or for the receptacle box to be receiving power from underneath. In the video I'm following, the transformer gets connected to some wires running into a little receptacle block, so that's more or less what I'm setting up here. So there we go. Finally, we have the motor with the magnet attached. Again, we have the laughable size, considering this device is supposed to generate 10 kilowatts, which is over 13 horsepower. In the video, the motor just has a ceramic disc magnet fixed to the shaft, so that's what I've done. I may not have the exact magnet selection that the maker of these videos has, but it really doesn't matter much. Would you be at all surprised if I told you that the way this too was done is just wrong and wouldn't work? These disc magnets have their north pole on one face and the south pole on the other. So each side is a magnetic pole, and the division between the poles is actually along the outer edge. Voltage is induced into a wire or coil as a magnetic field moves across it. If you just spin the face of one of these magnets next to the windings, you aren't really accomplishing anything. You have to sweep the magnetic field past the windings. Simply rotating a disc magnet like this, which is how this device and many others I've seen do it, it's, again, the absolute worst way to do it, and it is the least effective way possible. Really does almost nothing. But we're nearly done, so let's keep going. So now I've got the motor glued in place, and I've got wires run to it from my power supply. So at this point, we can power up the motor. Motor's spinning pretty good. So now let's plug in our lights and see if it works. Oh my gosh, it works. Holy cow. What do you know? The thing works. Just like that. Or does it? So let's just go ahead and turn the motor off. Uh-oh. The motor's off and the lights are still on. Well, let's just disconnect the transformer. Well, isn't that interesting? Did we break physics? Did we create infinite energy? No, I cheated. Just like the makers of these videos must, considering all we've gone over. If I open up my little box here, you can see I've got a small battery inside. And that's all there is to that. It would also be possible to have wires coming up through this little wooden board if I had a desk that I didn't mind drilling a hole in. You know, even if I were to rotate this like some of them do, you just rotate it around where the wires are coming up and that's no problem. But rather than doing any of that, I was able to replicate the results of being able to turn 3 lights on just by using a single tiny LiPo battery. But let's get the battery box out of the way and do some actual testing on this thing to see what, if any, output we're getting anywhere. Now, before we start the motor spinning, I'm just going to check some voltage a few places because, as you can see, even just from, picking up little bits of magnetism in the air, you can get readings all over the place with a sensitive meter like this. So just to verify that any readings we're seeing aren't being generated by this and are just kind of residual from the air, let's do some tests before we actually start the motor spinning. And in fact, we're going to have to do our tests with the motor spinning pretty quick because this magnet is actually reacting with this. There's this big magnet that's on the back here has, I could have set it up either opposing poles or attracting poles. Right now it's set up to attract. So this magnet is being attracted to this one back here, and it's putting stress at like axial stress on this, the bushings and stuff in this motor. It just after spinning for even a very short amount of time, it already sounds very unhealthy. So we're not probably going to be able to run it for very long before it just kind of destroys itself. But just to see, so we're on AC voltage right now. And now you can see actually just because of the windings of the coil that don't have any voltage on them, they've actually drained away, just the resistance through there has drained away a lot of the residual voltage. Because like if I put it to resistance here, you can see we're measuring the resistance through that winding, which is 51 ohms. And so with it connected, you drain away a lot of that residual. But now, residual voltage coming from this coil, again, 20, 30 millivolts. The middle ones, that's going to be a little bit tougher. I should change my leads really, but that's okay. We'll make it work. So on the terminals that go to the other side of the transformer, you can see again it's pulling that down, and we can read the resistance across that one, which is actually very low because that is the secondary winding, and that's the 12 volt side. So So, and then on DC voltage, I mean, again, we wouldn't expect to see anything when we're connected across these kind of things, other than just, bending that terminal a little bit, other than just, again, just residual voltage, very, very minimal. So let us spin this thing and see if we get anything at all out of it. Let's even bump the voltage up a little bit. Let's really make that motor hate us. So we've got no AC coming out of the transformer. What do we got on this side of it? Virtually nothing AC there. No DC there. What about coming straight out of our bearing coil? We've got essentially nothing AC and pretty much the same reading DC that we had just from open air. And we can verify that by just turning off the motor. And you can see that. You can hear that motor doesn't sound healthy. But yeah, you can see when I turn it off, it doesn't change. We're getting absolutely nothing out of this. So there you have it. To probably no one's shock and surprise at this point, nothing at all. I get nothing out of this machine. My fluke meter doesn't pick up even a few millivolts difference between the motor spinning or not spinning. It just doesn't do anything. And you might ask why I even bother making this video. Well, partly it's just because of the sheer audacity people have to put something like this together with either complete lack of knowledge of electromagnetism and electronics, or just the utter lack of F's to give about doing it in a way that makes any kind of sense. And partly it's because I hate the lies and misinformation that preys on people who don't have the background to recognize that these claims are garbage. I hate the idea that people are being misled. But I think the biggest reason was just seeing this particular contraption in a video. And I mean, all of these devices, their output claims, they're just utterly ridiculous. But this one just had so much fundamentally wrong that it was staggering. Rectifying the output with a diode, connecting it to a rectifier after that, connecting it to the wrong side of the rectifier, connecting that to a transformer, rotating a magnet in literally the least effective way possible, and then claiming that this pathetic abomination of a device could output 10,000 watts. I was just stunned at the ability of this device to get literally everything wrong in multiple ways. So I wanted to make a video about it. And finally, just for fun, I'm going to try to modify this thing to see if I can get anything at all out of it if it was set up in a way that made any sense at all. Okay, keep in mind, this isn't a great design. I don't think the windings are balanced. Everything's just kind of, it's hokey. It's not great. I'm not actually using the winding of this at all. You can see this, it's just this motor with some little permanent magnets around this little wheel and a winding on each side. The windings are actually connected together, so they're actually one circuit, and the other side of each of those, each of that coil comes to my meter, and you can see just barely picking up any kind of residual magnetism. And when I spin the motor, there you go. It's not much, 32 millivolts, not much, but it is definitely more than what the other one would do, and it's clearly a result. And I'm betting I can get more out of it if I spin it faster, but I'm also betting that the magnet will fly apart. But let's find out. Let's see if we can shoot one of those magnets off. Now look at that. We're up to almost 50 millivolts. The motor doesn't sound great. Three volts. 60 millivolts. And you know what? I'm not going to spin it any faster than that. That's too much. Eventually it's going to fly apart and that magnet's going to end up in somebody's eye. So sort of works, gets a tiny bit of output. It's not impressive. It's not efficient. It's not well done, but it does technically work. This is technically a small generator. Whatever this contraption was before just was not. It was just some random components thrown together to make it seem like it's something it isn't, so that they can get views and just trick you into thinking they made something, but they didn't. So I hope that was helpful. If you have any questions, let me know. And as always, thank you so much for watching. Take care.